I do want to ask you about the sharpest new shiny space telescope in the shed, which happens to be here, the James Webb Space Telescope, or JWST.
We already knew back then, in the late 80s, 1990s, that the universe was expanding.
Right.
And we knew that to see the very first galaxies, and maybe even the first stars that ever formed in the universe, because of the expansion of the universe, the light from those galaxies is likewise expanded, and it shifted from blue wavelengths to longer wavelengths, red wavelengths. And so the concept then for the next generation space telescope was to build an advanced telescope that really focused on the infrared part of the spectrum, because that's where we could see the first stars and the first galaxies. I knew that this telescope that was being built to probe the light from the first galaxies would also be a fabulous tool to study Neptune and Uranus. I mean, I just knew that because I knew it would be big enough. I knew that because it was a space telescope, the images would be stable and pristine. And I knew that these wavelengths of light in the infrared had all sorts of interesting molecular signatures so that we could learn about the upper atmospheres of these planets. And so I'm like, I'm in, I'll do this. So in 2002, I wrote a proposal saying, I would like to be an interdisciplinary scientist for this program to ensure that this telescope will be able to do solar system observations when it is launched. And in 2003, my proposal was accepted, and that was how I formally became involved in this telescope. So Webb, it's different than Hubble. It's a different kind of telescope for a number of reasons. One is it's a lot bigger than Hubble. So it's a 6.5 meter mirror, the golden mirror, the collecting area, versus Hubble's 2.4.
I mean, it's so big that it couldn't be launched looking like that. It had to be all folded up.
That's right. It had to be folded up. And that's why the mirror is segments.
Yeah.
So that it could be folded up.
Like a honeycomb.
Like a honeycomb, exactly.
But then it had to unfold in space. And I remember how nervous people were about this process because it really was something that every single step had to go right.
Not only did the telescope have to fold up, but if you look at Webb, it's got this huge contraption underneath it, which we call a sun shield.
Yeah.
And that's crucial for this telescope.
How did you feel as you were witnessing the deployment sequence?
I sure was nervous, just like everybody else. There were several single point failures where if that thing didn't unbolt or unfold, we didn't have a working telescope anymore.
Yeah.
So it was extremely nerve-wracking. But we had many years of testing because we knew that there was no fixing this telescope. This telescope's not in low Earth orbit like Hubble. The James Webb Space Telescope is 1 million miles away at a point called the L2 point. And it was put out there deliberately because it needed to be cold. It needed to have the sun shield to protect the telescope from the warmth of the sun, the warmth of the Earth, and even the warmth of our moon. So the sun shield is designed to be like an umbrella that protects it, a sun umbrella that keeps that telescope super cold. So we couldn't put it in low Earth orbit because it's just too warm in that environment. You can't sense infrared light when it's hot. You have to have it cold. By the way, that's also why this telescope is completely exposed to the elements of space. Most other telescopes have tubes that enclose them, and this one doesn't. The mirrors are just sitting out there.
They're just out there.
They're just sitting out there.
So the first deep field from JWST, I think the analogy I heard was that the image itself covers about the amount of space as a grain of rice on a fingertip held at arm's length. Is that right?
I heard a grain of sand, not a grain of rice.
Okay.
But it's the same concept, the piece of sky you see in that picture, if you were like standing in your backyard and looking up in the sky, that piece of sky is about the same size as a tiny grain of sand. If you moved your grain of sand over to the left, you would see those more galaxies. And over to the left again, more galaxies. And anywhere you look in the sky, it is filled with galaxies.
Just thousands and thousands in that one image alone.
Exactly. What I'm waiting for is the James Webb Space Telescope deep field, where we stare for days at a dark spot that we don't know where anything is. What are we going to see? And then think about that, going to be all over the whole sky. Our universe is going to mentally expand at that moment when we get that deep field from James Webb Space Telescope. It's going to be mind-blowing.
I just think about it peering so far back in time to the beginning of, the primordial cosmic murk.
Yeah.
When stars and galaxies are just starting to turn on, and how different the universe was, and the fact that we humans on this one little planet Earth can craft an instrument that has the capability to let us see that, 13.5 billion years ago, or whatever it ends up being, is really phenomenal.
Yeah, I view it as an example of what humanity can do when we work for the greater good. When we work as teams and we have a goal. This project required thousands of people in multiple countries, in multiple states, to take this vision and turn it into a concrete thing, this telescope, and then launch it on a rocket, and then have the ability to use it to probe, from right in our local neighborhood all the way to the edge of the known universe and everything in between.
Yeah.
It's amazing to me. And everybody had a role to play. I mean, the beryllium miners who mined the beryllium we used to make the mirrors, and the cable wrappers who wrapped the cables to allow this thing to move, and the people who, built the different instruments. We have a suite of 4 different instruments, cameras and spectrographs, both here in Europe. We all worked together. Canada. Canada made the fine guidance sensor that allows us to point this thing. I mean, it's a truly international effort, and it all comes together to create this revolution in how we see the cosmos.
Do you have a favorite among the images that have been released so far?
Well, they all have special aspects about them that make me go, wow. In a case of the image of the cosmic cliffs image, that's beautiful. It's like blue in the dark and orange in the bottom. And, I get excited about images like that because not only are they tremendously beautiful and evocative in a poetic way, but those are places where stars are being born.
Yeah.
And some of the little pokey things that stick out, that give it some of its dramatic structure, those are that's star birth in the making. And I think that's just so cool. And particularly when we use our infrared cameras, we can look inside some of those knobs and see the stars that are being born. And in some places, like the Orion Nebula, there was just an image released of the Orion Nebula. That's places where planetary systems are forming. We aren't seeing the planets, but we're seeing the swirling disks of dust and gas where those planets are being born. And even some of these galaxy images, while they may be static, like the Stephan's Quintet image, which is 5 galaxies, one of which is an interloper. It's a foreground galaxy. It's not part of the other crew.
Just wanted to be in the shot.
Yeah, it's just photobombing the other ones. But the 4 that are part of a cluster, what you learn from James Webb Space Telescope is that in the regions where they are interacting and overlapping, those regions light up in the infrared. Those are places where the dust and the gas and the existing stars of those other galaxies, when they are interacting, they are forming new stars. They are creating new realms of star formation. And they just light up in the infrared in that image. So, yeah.
And I just wonder, what's missing from that picture? What can JWST fill in? I mean, how much more color can it add?
What JWST adds to our ongoing story is it adds new wavelengths of light that we haven't had the sensitivity to study. And different wavelengths of light tell you different parts of the story. And we also use tools in astronomy called spectrographs. And that is where we don't just take pictures, but we actually take the light and we spread it out into its rainbow of colors. And what we do is we look for what we call fingerprints in that light, if you will. Certain atoms and molecules tend to absorb specific colors of light just by the very nature of their construction and their motion and vibration. They absorb certain colors of light. So by spreading the light out into a rainbow and looking for patterns in what light is missing, that tells you what molecules are there. And not only does it tell you what are there, it tells you their temperature. It can tell you their pressures. By tracking carefully these lines in the spectrum, you can determine the motions of this material. And so we don't just have a static picture. We can actually do like three-dimensional tomography of astrophysical objects by using this spectral light information. But as an astronomer, it's not just the pictures. It is spreading that light out and looking into its constituents. That's where the real deep science takes place. That's where you get, what are stars actually made of? Like helium, and the helium and hydrogen and beryllium and even iron and nickel. And how do you know that? You can't go there and weigh it. You learn it from the light.
Can you tell us about that instrument and what it might be able to show us about Uranus and Neptune and some of the other giant planets that we haven't been able to see before? How is this telescope going to help us understand these worlds?
Let's say you wanted to study Jupiter's rings, right? We know Jupiter has rings. Voyager saw them.
Right.
But we know most planetary rings change with time.
Okay.
Trying to image the faint ring of Jupiter next to the incredibly bright planet of Jupiter is extraordinarily difficult. The rings are 1,000,000 times fainter than the planet, and they're right next to it. But James Webb Space Telescope, the sensitivity is so good and the imaging capability is so good that the scattered light from Jupiter does not spread, even out to the local place where the rings are. So in our first images, engineering images of Jupiter that were taken just to test the scattered light on the camera, they took a couple of short images of Jupiter and moved Jupiter closer and closer to the fine guidance sensor to see if it would screw up our guiding.
Right.
Even in those short engineering images, the rings are right there. Beautiful, just totally resolved, right next to the planet 1,000,000 times brighter.
Well, can we talk about planets outside the solar system too?
Sure, yeah. What's your favorite?
What's your favorite?
Oh, I don't know. I got a couple of favorites.
Yeah?
I think a lot of astronomers, a favorite system right now is the Trappist-1 system.
Yeah, tell me about it.
Yeah, Trappist-1 is, that's the name of the star. Well, Trappist is the name of the survey, right?
Yeah.
But it looked at this star and it discovered that there are at least 7 planets orbiting this star. And most of those planets seem to be Earth-sized. In the Trappist-1 system, several of the planets are the right distance from the host star that water could be liquid on the surface of them. We call that the habitable zone.
Right.
And you and I could have a long talk about what habitability actually means. But, you know, in our solar system, at least on our Earth, the only place that we know life exists, there's a lot of water.
Yeah.
And so when we're talking about looking for habitable planets, we look at planets that are the right distance from their host star that they could have water on them. So that Trappist system, that we know that there are planets in potentially habitable region and that those planets are roughly Earth-sized, they are everybody's favorite right now for JWST to take a look at with our spectrographs.
Yeah. Do you think there is life beyond Earth somewhere? And if so, where?
Okay, so let me answer the second question first. This question of is there alien life out there, I usually break it up into two things. One is a thought experiment about the size of the universe, the scale of the universe, just how many stars there are in our galaxy.
Yeah.
And then how many galaxies. There's billions of stars just in our local galaxy. And there's billions of galaxies out there. And when you talk about whether or not life could have formed over the billions of years that our universe has existed with these billions of galaxies, each of which has billions of stars, I say life has to exist somewhere out there. Somewhere. Has to be out there. Does that mean that aliens have come to Earth and visited us? No. That's a totally separate question.
Yeah.
It's not a related question. All right. That's a more psychological question. I'm more interested in the science aspect of the question. I think we need to start with terrestrial sized planets that are the right distance to have water on them, because those are the conditions required to create life as we know it on Earth. And the only kind of life that we'll initially recognize is going to be life like ours, I think.
So JWST is one tool that we can use in the search for life beyond Earth, but there are others, including within our own solar system. Some of the rovers that are on Mars currently looking for signs of ancient biosignatures or ancient signs of alien life in the rocks there, but also some of the missions that are being planned to the outer solar system, and specifically some of the moons there. I'm curious about whether you think it's possible that life exists here in our local neighborhood, but beyond Earth.
Hey, anything is possible. I've learned in my career never to deal in absolutes because the universe is great at throwing curveballs at you. When we have our rovers on Mars and our orbiters that are doing really exquisite orbital imaging, it's clear that there's evidence that at one time there was liquid water on the surface of Mars. There's sedimentation, there's a chemical evidence, there's actually water trapped in the ices in the poles of Mars right now, and so it could very well be that at some time in the past that planet had liquid water and may have had the conditions for life to form. We don't know. It could be that life formed there first and transmitted itself inward to us. We could be Martians.
We could be Martians.
I don't know. We don't know the answer to that. Using our definition of looking at places where there's liquid water, people sort of initially confined it to a certain distance from the host star, sort of from the Earth, just barely out to Mars, and maybe inward a little bit, not quite as inward as Venus, but they kind of limited it to that region, saying, well, Earth is the Goldilocks zone, that's why it's not too hot, not too cold, that's why life is here. But we've learned more about our solar system with the spacecraft and telescopes. And one of the things that we have learned with our missions to the Jupiter system and the Saturn system is that some of the larger moons in those systems do have evidence of liquid water in their interiors. More water on Jupiter's moon, more water inside Jupiter's moon, Europa, than we have on the surface of the Earth, which is kind of crazy. Think about it.
It's mind-boggling to think about.
Yeah. The question is, could life form in that water? And it gets back to what are the ingredients you need for life. You need water, but you also need some kind of an energy source. You need some kind of a surface on which life can do its chemical thing to form. I'm not an astrobiologist, so I don't know what the right lingo is, but you need to have a surface for stuff to happen. And does Europa have those things? Well, it doesn't have them on its surface. Its surface is just ice.
Right.
But we know from our various flybys of this, we were able to map out its structure, its internal structure, by looking at the magnetic field and how it interacts with it, by looking at gravitational deflection. We know that it probably has a solid core. And we also know that Europa is warm. Now, why? Why would this moon out there at Jupiter's distance, why would it be warm, right? Why would Jupiter's other moon, Io, have active volcanoes? That's really warm.
That one is
that's
wild.
crazy warm. And the answer is these moons actually interact with one another. They do like a little resonant dance with each other as they orbit Jupiter. And as they orbit one another and interact with one another, their gravity of these moons makes very tiny flexes in the shape of the moons. But the flexes repeat over time, and that repeating warms the planet. I used to illustrate this for kids with like old credit cards. If you ever took
yeah.
an old credit card and you bend it, bend it, bend it, bend it, bend it, and you feel where you're bending, it's warm.
Gets warm,
It's
yeah.
really the same process. It's that flexing is what warms these. So for Europa, in orbit around Jupiter, we have the water, we have the rocky surface deep inside, and we have warmth. We've got this energy source thing. So is it possible that life is formed there? Well, yeah, sure. Who am I going to say no? I mean, what do I know? I mean, the universe is much more complex than I can imagine. And so we are building a spacecraft called the Clipper spacecraft, which is going to go to the Jupiter system and it's going to orbit Jupiter, but it's going to do multiple flybys of the moon Europa.
So Heidi, word on the street is that you have a favorite moon. What is it? And there's only one right answer to this question.
My favorite moon is Triton.
It's a pretty good one.
It's not the right one, though?
I was going to say Iapetus.
Oh, no. We're going to have to have a long conversation about that.
Tell me why Triton is better
All
than
right, so
Iapetus.
Triton is such a cool moon. It goes in a retrograde orbit backwards around the planet. We think it was actually a Kuiper Belt object that got too close
To-
to Neptune and was captured by Neptune. And it's a big moon. I mean, if you want Pluto to be a planet, I don't know where you stand on that issue, but Triton is a twin to Pluto, all right? So it's like a planet in orbit around another planet,
But it's going backward.
but it's going backwards around the planet. And when Voyager flew by in 1989, it actually flew kind of close, so we got a good view of one half of it. And it's got remarkable terrain, and it has active cryovolcanoes on it. There are volcanoes, ice volcanoes, erupting on Triton, like in real time. So that's pretty amazing. I mean, it's got an atmosphere, all right? And it could have a liquid water ocean inside it. So it may be an ocean world. And since we know it's active, because we saw it with Voyager, that may be another abode for life.
So Heidi, how did you become interested in astronomy? What was it that lit that fire for you?
It's kind of a goofy story, but I think in one sense I became an astronomer because I used to get carsick.
Seriously?
My family would go on road trips, and I would be in the back of the car, and I'd be so sick, and I couldn't read, I couldn't do anything except stare out the window. And at night, staring out the window, I started to recognize star patterns, like the Big Dipper and Orion, and I became more familiar with them because that's all I could do is to stare out at the sky. And so, I think that sort of kindled an interest for me. But I had a math teacher who one day took her class of 4 students aside and said, "Where are you young people planning to go to college?" And when it came to my turn, I said, Penn State. She said, "Why?" And I said, "Well, my dad went to Penn State. I live in Pennsylvania." She said, "I think you should apply to MIT."
Wow.
And I said, "Well, I don't even know what that is." So she encouraged me, and I applied. When it came time for letters of recommendation, I asked my chemistry teacher to write me a letter, and he said no. And I said, "Why not?" He said, "You'll never get into MIT." So I asked my history teacher instead, and she did write a letter, and I did get into MIT. And when I brought back my acceptance letter and showed it to my chemistry teacher, "Look, I got into MIT," he said, "It's only because you're a woman. They have quotas to fill." This is in 1978 when people said things like that to your face. That made me angry more than anything.
super
So
nice.
I was determined to go to MIT and graduate, you know.
What are some of the most nagging, unanswered questions in your mind that exist in astronomy, any field in astronomy? Could be anywhere in the universe, close to home, far away. What bugs you? What keeps you up at night?
How did the first stars and galaxies form in the universe? We have lots of models and theories, but to be able to make actual observations as early as we can, to tie together some of the disparate observations we have with a coherent story, I think that is an area that is very, very interesting right now. And of course, that's why James Webb Space Telescope was built, to add to a piece to that story. I think I'm also interested in how our planetary system that we live in, how did it in particular come to be, and how did it come to be habitable? We know this is the only system that we know is inhabited, right? Our solar system.
Right.
Is it required that you have giant planets in the outer system and small planets in the inner solar system to make habitability? Or is it just by happenstance? Did you have to have a Jupiter to make it habitable? Did you have to have a Neptune to sweep out through the Kuiper Belt and deliver volatiles to the inner solar system, water and stuff? I mean, that's so interesting, and it touches us as humans. Like, how did we come to be? It's part of our story. It's part of our life story. So I'm very interested in that question as well. And we still have so many observations left to make, both within our solar system and in the greater universe. I think astronomers will be busy for a long time to come.